Okay, welcome back to the afternoon session. We're going to have a short session this afternoon, just 2 talks, and then a longer break before the reception. So our first talk, joining us from Lausanne, is Raphaël Berthier, who will be talking about non-parametric convergence rates. Okay, Raphaël, thank you.
So thank you. Hi, everyone, and thank you for this opportunity to present my work. So yes, I'm currently a postdoc at EPFL, but today I will present work I've done before doing my PhD at INRIA in Paris. And so it's joint work with my PhD supervisors, Francis Bach and Pierre Gaillard. And so today I'm going to present one bond, essentially for LGD, so one convergence rate of stochastic gradient descent. And compared to what you might know, the challenge will be to prove something for what I call plain vanilla LGD, meaning that we will try to avoid some of the tricks that people use in order to prove bounds on LGD. So we will not regularize the objective and we will not take decaying step sizes, and we wonder if we do not do this, what can we prove? But okay, let me define a little bit the setting. So it will be supervised learning. You want to predict an output Y from an input U, and you have access to samples from the joint law of U and Y. You seek a function that minimizes the quadratic risk, which is the average square error between f of U and Y. Today, I will speak only about linear regression, meaning that I assume that the predictors that I seek are linear in some potentially nonlinear transformation of the inputs. So I will call phi the feature map, and I will seek function f theta of the form theta dot phi of u. And so now, because I'm going to do only, I'm going to look only at linear maps, I'm going to parameterize the risk R as a function of theta, just to make things simpler. So it sounds very naive, but as you know, it also incorporates kernel regression. So RKHS theory essentially tells you that kernel regressions are implicitly linear regression in some potentially unknown feature map. But what you have to remember is that in this case, very often the feature space will be infinite dimensional. So what I'm trying to do today is an analysis of LGD for linear regression, but in infinite dimensional spaces. So of course, the choice of your feature phi or the choice of a kernel, it indicates a very strong prior on the structure of your problem. And actually, it will define a regularity classes on your Hilbert space H. And so how do you define those regularities? You take the covariance operator of your features. So it's an operator sigma, and it goes from an infinite dimensional space to an infinite dimensional space. And you define the image of the powers of sigma. So the larger the power, the smaller the image, and this defines a nested sequence of subspaces of H. And these are spaces of regularity. So the larger the exponent, the more regular are the elements in the image. And so you can use that to measure whether something will be easy to learn or not. So for instance, assume that you are in the so-called attainable case, meaning that your risk is minimized at a linear predictor theta star. In that case, you will measure the regularity of this optimum by looking at the highest alpha, the largest alpha, such that theta star is in the image of sigma to the power alpha over 2. This gives you a number alpha 1, a real number, and this measures the regularity of the optimum. Similarly, you can measure the regularity of the features as alpha 2 being the largest alpha, such that the features phi of u are in the image of sigma alpha over 2 almost surely. And sometimes people call that under many names, but maybe like a source condition for the first one and capacity condition for the second. And so these notions are often used in non-parametric analysis, so in infinite dimensional spaces, in order to measure the performance of different estimators. And so classical work is a work by Caponetto and Debito. They analyze the performance of ridge regression, and they show that if the regularization parameter is chosen properly, depending on these two parameters and the number of samples, then the excess risk satisfies a certain bound. And they show that actually this rate is optimal for this class of problem. So today I want to present something different because I don't want to analyze ridge regression. I want to analyze stochastic gradient descent because it's heavily used in practice to reduce computational costs. And some people have already done this. So many people have analyzed SGD in a non-parametric setting. And the take-home message is that you can also reach the same optimal rates if you use a certain number of tricks, including decreasing step sizes, averaging, and regularizing. However, many people, like in practice, it seems that people are not using these tricks so much. And in simulation, it seems that theory overestimates the importance of these tricks. Maybe we do some of these assumptions because it just makes the proofs easier. And so we try in this work to do something completely different. We want to take plain vanilla SGD and see whether it works well or not. What do I mean by plain vanilla SGD? Well, you take your risk, you take the gradient of your risk, it's an expectation. And then this gives you stochastic gradients. And we will do single pass SGD on the data. We will not regularize, and we take a fixed step size. And we wonder how well can this work. And so we still use the same notion of regularity. And we get the following theorem. So we also control the expected excess risk. But now first, because we don't take decaying step sizes, we expect at some point SGD to take a random walk around the optimum. And so this is the term on the right, and this, the excess risk in this regime will be proportional to the step size that you have chosen and proportional to the risk of the optimal predictor. And before that, you will have a polynomial decay, and the rate will be the minimum of the two regularities plus one. So one of the two regularities will be a bottleneck for the fast convergence of the algorithm. So what can you use this for? So this is a toy example of how you can use this bound, and I'm going to take a nonlinear case, a kernel regression, to emphasize the fact that we do not do only linear regression. So in this example, we want to predict, we want to estimate a function here in blue, a function f star, and we observe it perfectly at random points sampled in the unit interval. And we wonder, can we estimate this function from the observation at random points? And we can take, in order to perform this estimation, something that you might want to call kernel SGD. And it works as follows. For instance, you start from the naive estimate, the function is constant equal to 0. So this is the left figure. And the middle figure, you see one update. You take a little kernel, so it's a bump function. You center it around the point that you have observed, and you just add a bump in order for your estimate to match the observation at the point that you have seen. And then you see new points coming in, and then you just update your function using the kernel, and you wonder, okay, how fast can this converge to the true function f star? So here is the result in that case. And here it will depend on the classical notion of regularity, which is Sobolev regularity. So if you assume that f star is in HR, so the Sobolev space of regularity R, and the kernel is in HS, you get a certain rate of convergence of fk to f star, which is, okay, polynomial, and you get the exponent, and the exponent depends on R, S, And so here on the dimension, so I put plots in dimension 1, but you can imagine estimation on the unit cube in general. And then, for instance, you can use these bounds to find what is the best kernel for SGD, for kernel SGD. So here, the optimal smoothness of the kernel happens to be the one that maximizes the exponent here, and it happens to be S equal to R. Same regularity as the function, and I don't know if this was obvious from the start. Okay, take-home message. We give rates for LGD depending on non-parametric quantities, and this rate make appear a trade-off in the choice of the kernel, a trade-off between the regularity of the epsilon and the regularity of the features. In the case where there is low additive noise, so maybe you want to call that the interpolation setting, so the risk of the optimal predictor is close to 0, then plain vanilla SGD will converge. And you can even achieve fast rates if the problem is regular. Let me end by thanking my collaborators, so Francis and Pierre, and thank you for your attention.
Any questions? Actually, can you go back to the 2 slides, I think, with the optimal smoothness? So if I understand correctly here, the smoothness, the behavior and the smoothness, is there something to balance the choice of smoothness? Or if I choose it to be even smoother, it seems, sorry, I guess just choosing less smooth. I mean, when you say that optimal is S equals R, things become worse if on either side of it, because I'm.
Yes. So in this problem, you don't choose R because it's a problem. You choose S. Yes. Right? And so here you have a minimum between 2 quantities in the exponent.
Oh, okay.
And one is increasing in S and the other is decreasing in S. And so there must be a point where the maximum is achieved.
Yeah, sorry, I missed the negative sign there. I didn't see that it was a balance. It looked like both went in the same direction. Thanks. Okay. Yeah, Andrea.
A small question. The big O and small O here is constant D and then to infinity. That is the setting.
Okay. Big O, small o. Okay, so
here you are keeping dimension D constant, fixed, and then you're letting n to infinity. That's
yes. So everything is for n to infinity, and yes, small o in the exponent, because I think yes, we just show something for if you compare to, like, if you had an exponent epsilon, you remove epsilon from the exponent.
Okay.
Other questions? Okay. Thanks for getting us almost back on track in terms of timing. And that's our next.